I'm Armon, and today I want to spend some time talking about Vault. So when we talk about Vault, the problem we're really talking about solving is the secret management problem. And so when we start talking about secret management, the first question that naturally comes up is, what is a secret? So when we talk about secret management, what we're really talking about is managing a set of different credentials, right? And so what we mean when we talk about these credentials is anything that might grant you authentication to a system or authorization to a system, right? So some examples of this might be usernames and passwords. It might be things like database credentials. It might be things like API tokens. Or it might be things like TLS certificates. The point is, any of these things, we can use these to either log into a system and authenticate, such as a username and password, or we're using it to prove our identity, something like a TLS certificate, and so we're using it to authorize access potentially. So all of these things fall in the realm of secrets, and these are things we want to carefully manage. We want to understand who has access to them. We want to understand who's been using these things, and in the case of most of these, we want some story around how we can periodically rotate these. And so when we look at the kind of state of the world of how these things get managed, in practice, what we see is secret sprawl, right? And what we mean by secret sprawl is that these end up everywhere. They're in plain text inside of our source code, so maybe it's hard-coded in a header what the username and password is. It ends up inside of things like configuration management. So again, this is living in plain text in Chef or Puppet or Ansible, and so anyone can log in and see what these credentials are. And ultimately, all of this typically ends up living in a version control system like GitHub or GitLab or Bitbucket. And so these things end up sort of strewn about or sprawled all over our infrastructure. And so what are the challenges with this world? Well, we don't really know who has access to all of these things. So we don't know, does anyone in our organization with access to GitHub, can they log in and see the source code and thus see what our database credentials are, right? And even if they could do it, we don't know if they have done it. We have no audit trail that says, just because Armon could have seen that secret, did he go on and access it? So we really have no fine-grained ability to manage who has access or to even audit who's done what with it. Worse yet, how do we actually rotate any of these things? So if we realize we do need to change our database credential, there's been a compromise, or we're doing a periodic rotation, it's very, very difficult if we're in a place where it's hard-coded in our source code, or it's strewn about in so many different systems that it's really difficult to really know how to effectively do this rotation. And so this state of the world is what we refer to as secret sprawl. And so one of our first goals when we started working on Vault was to really look at this problem and say, how can we improve it? And so this is really where Vault came from. So Vault really starts by looking at the secret sprawl problem and saying we can only solve it by centralizing, right? So instead of having things live everywhere, we move all of these secrets to a central location, and Vault promises that we're going to encrypt everything, both at rest, inside of Vault, as well as in transit between Vault and any of the clients that want to access it, right? And so this gives us a few properties. One, unlike these systems where we were storing this stuff in plain text, at least now if you could see where the secret is stored at rest, it's encrypted. So you don't get implicit access to just be able to see this secret. The next thing is Vault lets us overlay fine-grained access control on top of all this. So instead of it being anyone in our organization who has access to GitHub and can see the source code, now we can go much more fine-grained and say, the web server needs access to the database credential, the API server needs the API tokens, but everyone shouldn't have access to everything. And then on top of this, we have an audit trail. So now we can actually see what credentials did the web server access, what credentials did Armon access from the system. And so we have much more visibility and control over how these things are all being managed. This is sort of the level 1 challenge with Vault, is at least moving from a world of sprawl, where things are everywhere, to a world of centrality, where we have sort of strong guarantees that it's encrypted, strong guarantees around who has access, and strong visibility into this. So this becomes our first level thing. The next level challenge becomes realizing who we're giving these credentials to, right? So great, we've stored all these credentials safely in Vault, and now we're going to thread these out and provide it to an application. The challenge is applications do a terrible job keeping secrets. Inevitably, the application will log its credentials out to a logging system, so it might write it out to standard out. This gets shipped off to Splunk and is now in a central log that anyone can see. It shows up in any sort of a diagnostic output. So maybe our application has an exception and it shows the username and password in the traceback or inside of an error report. It might be shipping it out to external monitoring systems when there is an error. And so in general, what we find is applications do a poor job keeping things secret. So even if we do a great job centralizing it and strongly controlling it and encrypting it on the way to the application, the app isn't trusted. So one of the second level capabilities Vault introduces is what we call dynamic secrets. And the idea behind a dynamic secret is instead of providing a long-lived credential to the application, which it inevitably leaks, we provide short-lived ephemeral credentials. So these things are dynamically created, but they're ephemeral. So we might only give a credential to an application that's valid for, say, 30 days. And the value of this is a fewfold. Now, even if the application leaks this credential out, it's only valid for a bounded period of time. So it might write it to a logging system and that becomes visible, but we create a moving target for an attacker by constantly revoking and issuing new certificates. The other thing that's valuable is now each credential is unique to each client. So previously, if I had 50 web servers, all of them would come in and read a static database credential. And so this means if there's a compromise and that database credential gets out, it's very hard to pinpoint where the point of compromise was. There's 50 servers, they're all sharing the exact same credential. Versus in a dynamic secret world, each of those 50 web servers had a unique credential. So you know very specifically web machine 42 was the point of compromise, right? The last thing that this lets us do is have a much better revocation story. So now if we know web machine 42 was our point of compromise, we can revoke the password, username and password for just web machine 42 and isolate that leak. But if all 50 machines were sharing the same username and password, the moment we try and revoke it, we'd cause the entire service to have an outage, right? So the blast radius of a revocation is much larger when you have a shared secret versus a dynamic secret. The third challenge we found was that applications are often storing data ultimately. And so the challenge becomes, right, how do the applications protect their own data at rest? Because we're not going to be able to store all information within Vault. Vault is meant just to manage secrets, not anything that might be confidential. So what we often see is that when Vault is being used as a centralized sort of secret management store, people are storing encryption keys. So we might put an encryption key inside of Vault and then distribute that key back out to the application. The application is doing cryptography to protect data at rest. What we find, though, is applications generally don't implement cryptography correctly. There's lots of subtle nuances, and it's easy to get wrong. And with these kind of mistakes, oftentimes it compromises the whole cryptography when those mistakes are made. And so one of the challenges we often look at is how do we get away from Vault just storing an encryption key and handing it to the application and assuming the app will do cryptography right? So this has evolved into a capability that Vault calls encrypt as a service. And the idea here is instead of expecting that we're just going to deliver a key to a developer and the developer implements cryptography correctly, Vault will do a few things. One is it will let you create a set of named keys. So I might create a key that I call credit card information, and a separate one I call social security number, and one for PII. And these are just names. I'm going to just name this key, and I'm not going to actually give this value out. But then what we expose is a set of high-level APIs to do cryptography. So these APIs will be kind of the classic operations you expect, right? Things like encrypt or decrypt or sign or verify. So now, as a developer, what I'm really doing is calling Vault with an API and saying, I want to do an HMAC using my credit card key and some piece of data, right? And what Vault is shielding is the implementation is being provided by Vault, so we don't have to trust that the developers implemented these high-level operations correctly, and the key management is also being provided by Vault. The developer never actually sees the underlying key. This lets us do a few things. One, it ensures that the cryptography is correctly implemented because we're using a vetted implementation by Vault. This implementation is vetted both by us, by the open source community, and by external auditors that we use. It also lets us offload key management. So if we think cryptography is hard, key management's even harder. And so in practice, when you ask how many applications properly implement key versioning, key rotation, key decommissioning, and the full life cycle of key management, the answer is very few because it's challenging. But by offloading this to Vault, we can actually use high-level APIs to do all of this. So we get the full key life cycle as well provided by Vault. And so in practice, these end up being the three major challenges that we're trying to help developers with, right? How do we move these credentials out of plain text and sprawled across many different systems into a scenario where they're centrally managed with tight access control and clear visibility? to then how do we go even further and protect against applications that aren't necessarily to be trusted in keeping secrets. And we do this by being ephemeral. So we create this moving target where what we're really managing is that the web server should have access to the database, and that credential that enables it is a dynamic one instead of static. And then lastly, how do we go further in helping the application protect its own data at rest? And that's done through a series of key management and high-level cryptographic offload. So these three are kind of the core principles of Vault. So now maybe we'll zoom in quickly and talk a bit about high-level architecture of how does this actually get implemented. So when we talk about Vault's architecture, there's a few important things to realize. One is that Vault is highly pluggable. It has many different plug-in mechanisms. So when we talk about Vault, it has the central core, which has many responsibilities, including sort of the lifecycle management, ensuring requests are processed correctly. And then there's many different extension points that allow us to fit it into our environment. So the first one that's extremely important is the authentication backends. These are what allow Vault to allow clients to authenticate from different systems. So for example, if we're booting an EC2 VM, this EC2 VM might authenticate using our AWS authentication plugin. This plugin allows us to tie back into Amazon's notion of identity to prove that the caller is, for example, a web server. But if we have a human user, they might be coming in and using something like LDAP or Active Directory to prove their identity. If we're using a high-level platform, maybe something like Kubernetes, we might be using our Kubernetes authentication provider. And the goal of these authentication providers is to take some system we trust, whether it's Kubernetes, LDAP, or AWS, and use this to provide application or human identity. At the end of the day, that's what we're getting out of this, is a notion of the identity of the caller. This is great, and then we use that to connect to an auditing backend, which allows us to connect and stream out request response auditing to an external system that gives us a trail of who's done what. So this might be, Splunk as an example, where we're going to send all of our different audit logs. Vault will allow us to have multiple different audit logs, so we can also send to Splunk, as well as a system like syslog as an example. The next level challenge is where does Vault actually store its own data at rest, right? So if we're going to read and write secrets to Vault, it needs to be able to store these things somewhere. And so these are what we call storage backends. So storage backends are responsible for storing data at rest. So this can be really a couple of different things. It could be a standard RDBMS, MySQL Postgres. It could be a system like Consul. It could be a cloud-managed database like Google Spanner. But the goal of these backend systems is to provide durable storage in a way that's highly available so that we can tolerate the loss of one of these backend systems. The last bit is how does Vault provide access to different secrets? These are the secret backends themselves. And so these come in a few different forms. So the biggest use of these is to enable the dynamic secret capability we talked about before. So one form of secret backend is a simple one. It's just key value. So I might just store a static username and password in there, and I'm giving it a username and a password, and these things are static. And this is just a key value store that's encrypted at rest. However, as we get more sophisticated, we might want to use the dynamic secret capability we talked about. And so that is where these different plugins start coming in. So we have different database plugins. So database plugin will allow us to dynamically manage MySQL and Postgres and Oracle and et cetera credentials. We have things like RabbitMQ. So maybe we're doing dynamic credentialing for our message queues. But this kind of goes on. You can even apply the same principle to something like AWS. We might have applications that need to read and write from S3, but we don't want to give them long-lived access to IAM. So instead we define a role in our AWS backend, and we'll go and dynamically generate short-lived credentials as needed. So this extends that sort of dynamic secret paradigm. So this is an extension point that allows Vault to apply this same principle to many different things. One common use of this is PKI. So in practice, certificate management tends to be a nightmare, and what we often see is very long-lived certificates, maybe 5 to 10-year lived certificates, because we don't want to go through the process of generating them. Versus with Vault, we can define them and programmatically generate it. So in practice, people use very short-lived certificates, maybe as short as 72, 24 hours, and this way you're constantly moving and creating a moving target. This list sort of goes on. It includes things like SSH as an example, so we can broker access to SSH as well, so you don't have a single PEM to rule them all across a large state of machines. So at its core, this is what makes Vault so flexible, right? It allows Vault to manage clients that are authenticating against a different set of identity providers. We can audit against a variety of different trusted sources of log management. We can store data in almost any durable system. And then we can extend the surface area of what types of secrets can be either statically or dynamically managed by adding new secret backends. So this becomes Vault in a single instance nutshell. So as we talk about running a Vault instance, each instance of it is one of these. And then in a broader deployment, what this will look like is we run multiple Vault instances to provide high availability. So at the highest level, we'd have a shared backend. For example, this might be console, which internally is 3 different servers as an example, providing us HA. And then we'll run multiple vaults in front. And what Vault does is it'll coordinate with the shared backend to perform leader election. So one of these might be elected our current leader. And so as a client, when we're making a request, we're talking to the leader. And even if we talk to sort of a non-leader, we'll be transparently forwarded to the active leader. And so in this way, if any particular node dies, power loss, process crashes, maybe network connectivity is an issue, we will detect this, promote a new one to leader automatically, and this instance takes over active operation. And our other secondaries will begin to promote. And so this is what Vault looks like at a high level. It operates as sort of a shared network service, and we're talking to it just as an API client over the network. So what Vault typically exposes is a RESTful JSON API. So it's JSON over HTTP, making it relatively easy to actually integrate with our applications. I hope this was useful as a high-level introduction to Vault, and please check out our other resources to learn more. Thank you.